Hello, welcome to Agora, where we talk about the world through the lens of Christianity. I am your host Isaac, and today we are going to talk about black holes with Tyler Knowles, 黑洞. Hello everyone, 大家好. We are here with Tyler Knowles, who is a friend of mine and a student at Westminster, where I am currently studying. So I've invited him to talk about something that he likes very much, that is close to his heart, and also that is related to the Christian faith in some way that he wishes to talk about. Yeah. So Tyler?
Yeah, thanks, Isaac. It's really great to spend a few minutes with you today, and I get to talk about something near and dear to my heart, something amazing, while also being pretty mysterious
很神秘
for us. Yeah. And human beings have always been captivated by things that are mysterious or uncertain.
Captivated, 被注迷
Things outside of our control, or things that are chaotic, can't be planned.
Chaotic.
So in ancient times, of course, there was much more that seemed to be chaotic or uncertain. Just how was it that the sun rose? Where does rain actually come from? Just what are those big monsters in the sea that all the tales are told about?
Moby Dick.
Right.
Yeah.
And we have answers to those questions today. Those things are pretty well understood. But there's, of course, much in the universe that we still don't really understand very well. And one of those things is black holes. And so that's what I'll...
Black holes. 黑洞. Black holes.
That's what I'll spend a little time speaking about today.
Interesting.
So just for a little personal background, in a former life, and by that I mean almost 10 years ago, I was studying under a computational astrophysicist.
Astrophysicist, 天文学家,天文物理学家.
Yeah, so just a fancy way of saying that my research advisor at the time specialized in speeding up computer programs for scientific applications. And the application I worked on specifically was colliding black holes.
Colliding black holes. So is that like what NASA has been talking about lately, or some experimenters have been talking about?
Yes, it's
recently
been
with
it's been about a decade now. Again, when I first came on the project in 2016, the first positive detections of black hole collisions had been made just right around that time. And there's been some exciting things since then. I think one of probably the most exciting was the colliding neutron stars, actually, which I didn't work on directly. But those are a little bit more interesting because we know more about the neutron stars already. So
probably
we can
study them
a little better. Because we can see them, we have a better understanding of exactly how the physics works when it comes to a neutron star. The black hole is, as of yet, pretty much completely mysterious. We don't know what the makeup of a black hole is. What is it really? What's really in there? We don't know.
Are neutron stars like kind of are they on their way to becoming a black hole, or did they ever become a black hole?
Neutron stars would only become a black hole if they got sucked into a black hole. So a neutron star is a dead star, so nothing's really going to happen to it unless acted upon by something else. A black hole is also a dead star. Just a much bigger dead star. So small stars can become neutron stars, small stars can become neutron stars when they die. The larger stars will become the black holes.
There you have it. Neutron star 就是中子星。So 他们就是比较有被研究过的，大家比较看得到的，所以是也可以有研究过的。Okay. So what can you talk? How can you introduce these black holes to us?
Sure. If we jump back well over 100 years, a couple hundred years at this point, actually, you probably have heard at some point, no matter whether you've studied science a lot or a little, that Newton discovered gravity when he was sitting under an apple tree and the apple fell and hit him on the head.
Yeah.
No doubt an apocryphal story. Most likely not true, but
蝶文轶事
a story that we nonetheless tend to tell ourselves regularly, and makes for a fun
I always believed in that
a fictitious history. I don't think it's true. Maybe it's true, but I don't think so. And so even still, we take gravity for granted. Humanity seems to have always taken gravity for granted, but if you stop and think for a moment, you'll realize just how bizarre it is that everything is just pulled down to the earth. There's no this in the normal course of things, there's no reason for everything to be pulled towards the earth. The desks we're in, the chairs, pencils, if we had a pet dog ourselves, everything's being pulled down towards the center of the earth.
We're so used to it that we don't.
We're so used to it.
Don't even question it. It's like a fact of life.
Right. Yeah. But even though we can stand up, right, we're not stuck permanently in one place on the surface of the earth. Even though we can jump, of course, even ride in airplanes, eventually we keep coming back down to Earth. And this happens pretty much the same no matter where we are on Earth. Now, of course, we can escape the Earth's gravity. We can get in a rocket ship and fly high enough that we're free to float around, as they say, in space, right? Or
satellites.
In free fall, right?
Yeah.
But even the moon, which is pretty big, at least in comparison to humans, is trapped by the Earth's gravity. And but the Earth and the moon together are trapped by the sun's gravity. So it is a pretty interesting and, when we stop to think, perhaps bizarre
Everything's
thing.
trapped together.
Everything is
pulled together.
Yeah, everything is trapped together. And that's more or less what Newton told us when he described gravity. Gravity is a force that attracts any two objects together, any objects with mass. For those of you who have studied a little physics. So even the two of us around the microphone right now do have a gravitational attraction between us. It's just so small that neither one of us can feel it. We're both feeling the pull of Earth's gravity because Earth's gravity is so much stronger than the gravity that either one of us have.
地心引力、万有引力
Yeah, and so it's just always kind of pulling us down, even if we can't really feel it. We stand up without thinking about the fact that we're kind of disrupting gravity and going against it.
Just too used to it.
Yeah. And so when Newton described gravity as a force pulling two things together, that was very good for physics students and engineers for the most part. Helps us describe how the planets move around the sun, those types of things. But it's not really the whole story because Newton told us that gravity pulls things together. He didn't tell us how they're actually being pulled together.
The why and how.
Yeah, what is it that's actually pulling these objects together? Because we have an intuitive notion of a force. When we're sitting in our cars, our seatbelts, of course, are strapped around us, and so literally being wrapped around us are keeping us inside the car as we drive around.
Pretty tangible. Yeah.
Right, and if we're in our socks, we can slide across our slippery kitchen floors, and we know that there's friction between our socks and the floors. Of course, if you miscalculate, you'll smash into the refrigerator. That's the force of you hitting the refrigerator. That might happen if we're not careful.
And we get an equal reaction.
Right, exactly. We get an equal reaction. But gravity's not a force like any of those things. There's no seatbelt keeping the moon attached to the Earth. There's no friction between the Earth and the moon per se. Earth and the moon aren't even attracted magnetically. When you smash into your fridge, maybe you knock off one of the magnets, right? But there's not a magnetic force there. So there's something unseen, unfelt going on, but that can act at very, very long distances, right? It takes light something like 5.5 hours to travel from the sun to Pluto, and Pluto is still, no matter whether you consider Pluto a planet or not, it's still trapped by the sun's gravity without a doubt. So something invisible is acting at very long distances.
And light also, or gravity also like travels to Earth in like what? I heard it was like 8 minutes or 10 minutes, or something.
You mean for light traveling from the sun to Earth?
Yeah, or like gravity, the gravitational.
Oh yeah, so yes, even so, gravity, in some sense, I can touch on this a little bit later, travels at the speed of light. So it would take about this. If the sun suddenly went dark, not only would we not know because the light for 8 minutes, but the Earth would keep traveling its happy trajectory for those 8 minutes, and then after that would.
There you have it, folks.
Would fly
Gravity
off.
is not an instant.
It's not instant, right?
Wow.
And Newton certainly didn't tell us that either. Everything that he had written down was not time dependent. Yeah.
Time dependence. Oh, that's another.
So there actually is some time dependence. But all of that information had to wait until Einstein, almost 200 years after Newton, when Einstein finally was able to tell us what gravity actually is. And what he said was, and don't get scared when I say this, but what he said was that gravity is the curvature of space-time.
Oh, the curvature, 曲率曲度, the curvature of space-time, 是时空的曲率. What is the curvature of space-time?
Yeah. What is curvature? What is space-time? Those are great questions.
Wow,
so
getting so esoteric.
Yeah,
when I was mean?
the best illustration that I think I can try to describe without drawing a picture is when I was a kid. And so sometimes today when you walk into Walmart,
all right, Walmart.
When you're checking out, the cashier will ask you if you want to round up to donate to one of the local children's hospitals.
Walmart 就是个便利商店，像我们的 7-Eleven 或是那个 Family Mart.
Yeah. So when I was young, before Walmart came to our town, we had Kmart.
Kmart.
Another big store similar
marts,
to Walmart. And sadly, I think they're mostly being pushed out now by Walmart. But
oh no.
But in any case, instead of the cashier asking you if you wanted to round up to donate, there would just be a big bin sitting close inside the door. And basically there was a huge funnel on top of this bin. And there was a little slot on the edge of the funnel so that you could put your coins in there. You could put your quarter in there. And the quarter would roll on its edge all around this funnel and keep rolling, getting further in, further down,
so
faster,
it's a funnel,
faster.
A漏斗, yeah. 漏斗.
Until the coin just fell into the bin. Yeah.
一米就绕着这个漏斗，然后就这样慢慢的掉落到这个洞里面。
Yeah. And so that's
fun. Yeah.
That's actually a good illustration of gravity. So what's happening is the sun is sitting out in space and it's warping space around it. Now we tend to, I should say, when I say space-time, when we say space, we think out there, empty, cold space.
空荡荡的 space, yeah.
It is cold and fairly empty, but space itself is actually a thing. I said before that we don't think about gravity as kind of pulling us down like a heavy blanket, but what we call empty space is itself kind of like a fabric, not a blanket you would lay on your bed, but kind of a blanket that maybe fills up your whole room. You can still move through it, you can push it out of the way, you can twist it, and
so it's like an entity. It's like
it is actually an entity.
An entity of itself.
And so anything with mass will bend the space around it. You can imagine. So a blanket's harder to imagine, but maybe a room full of those like little plastic balls, like the play pens at McDonald's.
Yeah.
Right, you can kind of wade through. So
塑胶球.
Space is something that we can walk through and move through. And so what the sun does is it kind of bends. You can imagine the sun sitting at the center of the funnel, and so the space is bending around it, and the Earth is like the quarter, riding the edge of this curve, going around and around the sun. And thankfully the Earth has enough momentum, we're not going to fall into the sun anytime
goodness.
soon, but,
I don't want to fall into the sun.
We don't have to we don't have to worry
it's
about
hot
that.
enough in the summer, yeah.
Right. Another illustration that's good is imagine yourself standing in the middle of a trampoline. The fabric of the trampoline is now sort of bending toward you. So I could put a quarter on the edge of the trampoline. It would go around the edge and eventually fall into you because the fabric is warped
这种
toward
弹
you.
跳板或弹跳网，就是中间有 trampoline， 就是那个弹跳板。Yeah.
So the moon is riding around the Earth's dimple. The Earth is riding around the sun's dimple. I'll probably say dimple now instead of funnel.
Dimple 酒窝 yeah 脸上的酒窝 dimple.
Yeah. And basically, the bigger something is, the bigger dimple it's going to make in space. For those of you who have studied this, you've probably heard something that we say often. Matter tells space how to curve. Space tells matter how to move. So without the sun sitting in it, the space is just sitting there doing nothing. You put the sun in, all of a sudden the space begins to bend and curve toward the sun.
Could you say that again?
Yeah, matter tells space how to curve.
Matter tells space how to curve.
And space tells matter how to move.
Space tells matter.
So the sun is bending the space around it, and the Earth gets to ride on that curved space. And of course, both things are going on at once because the moon is traveling around the curvature caused by the Earth. Both of them riding around on the curvature caused by the sun. And so that's the equation that Einstein wrote down for us. If you ever actually see it written down, it looks very simple. There's one term on one side, and then on the other side is another term with just a couple of constants, 8 pi g, things like that.
Heard they're kind of like complicated things called tensors.
Yeah, they are complicated things called tensors. So it looks simple, but depending on how many dimensions you want to put in there, you're actually working with like 16 equations.
Okay. Oh wow, okay.
Yeah,
16 equations.
Yeah, it's 4 by 4. So there's 4 dimensions. Usually when we think of space, the 3 spatial dimensions we're used to, front and back, left to right, up and down.
Yeah.
But then a time dimension.
A time dimension.
So now
wow, there's
time.
40 space-time there.
Right, yep.
张量 tensor, 张量 tensor.
So each of those tensors are going to be 4 by 4 tensors, 16 entries.
哇，那就4乘以4的这种张量，所以里面有16项。Yeah. Oh.
Yeah, and so one side of that is telling you what is the shape of the space-time, how is it curved, and the other side is describing then how matter and energy are distributed in that space-time. So those two things are affected by one another. And so that's all fine and good. But we said we were going to talk about black holes. So
let's come back to the black holes.
What does this really have to do with black holes? Well, you've probably heard that black holes suck everything in and nothing can escape. That's another way of saying that black holes have just a lot of gravity. They make very big dimples in space-time. So we've already said, despite the fact that for most of our lives we're trapped here walking on the face of the Earth, we could get in a space shuttle and fly far enough away that Earth's gravity wouldn't affect us. That's not an option in a black hole. Anything that gets close enough to the black hole can never go back out. If you and I wanted to travel close to one, we could never escape. Light even actually gets trapped by a black hole,
and that's why they're
can't escape.
Black.
And that's why
that's why they're black.
Right? We see things because light is reflecting off of all of those objects into our eyes. And if the light's getting sucked into the black hole, then no light is bouncing off of it, being radiated out of it. Right. So the best we can do is just kind of look around it, so to speak, which is interesting in and of itself. I wasn't part of this work, but of course a couple of years ago, there was finally a good picture of a black hole. A lot of
one of the
telescopes together
they pieced together all the images. That was incredible.
It was incredible, in part because it was so similar to what we expected.
The predictions.
Which is always amazing. We have, as much as we don't understand about black holes and gravity, we do actually have a pretty good grasp from our own experience here on Earth. We can tell pretty well what's going on way out there in space, which is amazing in and of itself.
That's true.
Yeah, so black holes are, we already said dead stars, and I'm not much of a stellar astronomer, so I don't
Stellar.
I don't quite remember all the mechanics of stars when they die. Yeah. So multiple meanings of stellar there, but
we have it in Chinese too.
Yeah.
明星系.
But we know that planets orbit stars. Some planets orbit one another really closely. So I always said if Pluto did get put back on the planetary list, we'd have to include her sister, because Pluto
has a sister.
Share it. Yeah, they're both about the same size. They actually orbit one another, and both of them together are orbiting the.
Are they like what they call like twin? Is that twin star or something, or twin something?
Something like I don't. Yeah.
Not sure.
Something like that.
Or like a twin system, twin planet
right.
system.
Yeah, definitely. Yeah. It's definitely a binary system.
Yeah, a binary system. Yeah.
And so many galaxies have black holes at the center, lots of things swirling around them. And so there are places in the universe where two black holes are orbiting one another, spinning around one another very quickly. So if you think back to the trampoline analogy, now instead of just you standing in the middle, you have a friend, and you both are standing there on the trampoline. And you can kind of imagine that if you and your friend started running in circles around one another on the trampoline, all of the trampoline fabric would bounce up and down a lot, and you'd probably actually see, if you could go really fast, you and I maybe couldn't go this fast, humans maybe couldn't go this fast, but if you went really fast, the fabric on the trampoline could actually maybe ripple out towards the edge from where you're running around each other. And so two black holes, huge dimples or funnels, if you want to think of them, of gravity, as they orbit around one another, the space-time around them gets very warped and compressed and stretched and twisted. And
this is like because of the speed they're evolving.
Yeah. So, I mean, even if they're moving relatively slow, there'd still be some amount of waves,
maybe not as
ripples
big
from them, but certainly not as big. Certainly not big enough that we could detect them.
Yeah, 没办法侦测到，太小了。
Yeah, but in the last seconds before two black holes collide, they're going around each other pretty quickly. In fact, relatively close to the speed of light in comparison to human terms. They're not quite at the speed of light.
Oh, wow, they can reach that fast.
They're very fast.
Like what, 90%?
Oh, boy, that's a good question. I actually don't remember. Over half, I think.
Over half. That's pretty impressive.
So still very impressive.
For heavy objects, that is impressive.
So the gravity around, the space-time around them is just kind of churning. And so that's making enough of a ripple. There's actually ripples in the gravity, kind of compressions and stretches in the gravity that are rippling out from that. And then, of course, they collide and everything kind of settles down after that. But here on Earth, we can detect like that last second, sometimes the last couple of seconds, depending on the system.
It's a pretty long wave there.
Yeah. We can detect those stretches and compressions that are coming out of these collisions. So there's really big ripples in space. And so you can go online and look at the LIGO scientific collaboration.
LIGO, L-I-G-O. Yeah.
And Virgo, V-A-R-G-O.
V-A-R-G-O.
These are big interferometers. You can look up how those work. Basically, what these interferometers do
干涉仪,
is they measure, like, so when those ripples in space that are coming out are actually kind of shrinking and stretching space a little bit, and so these interferometers use light to detect the fact that distance is actually changing a little bit as these gravitational waves pass through Earth, and indicate to us that somewhere way out there, two black holes collided in space. Which is pretty
so you can actually tell like where it is.
Because we have multiple interferometers, we can triangulate to see where in the sky this happened.
Nice.
And so we've had some, I think especially with the neutron stars, then we were able to turn some other telescopes in that direction and catch some other, like some radiation bursts that were coming out of the sky at that same time. So very good collaboration, very good event for people studying numerous different things to have all of that data together.
Yeah, wow. Telescope. You've gone far away from what, Galileo, or who was it?
Yeah,
Kepler.
I mean,
Kepler.
probably further back than that.
Yeah.
I mean, yeah, human beings. I actually don't know the history of lenses that well. I don't know when human beings were.
Kepler was like observing all these.
Oh, observing.
Yeah,
certainly.
He had that telescope.
And so now there's telescopes pointed at the sky.
Yeah.
All the time, collecting so much data. Yeah.
Interesting. Wow. Wow. I mean, yeah, that's a lot of new stuff I've actually heard about this gravitational wave, how it's actually done.
Yeah, there's great illustrations online that can show you how the interferometers work, with some more technical detail, like how we're measuring the strain, it's called, for these gravitational waves.
Strain?
Yeah, it's called a strain. So it's more like a sound wave than it is a water wave. So water just kind of pushes itself along completely. Sound, right, is a compression and a stretching. The gravitational waves are more like sound waves in that respect. Than like a water
that's like
wave.
different from how they're usually pictured. Like usually they're pictured as water rippling.
Well, it's easier to see the water ripples.
That's true. Yeah.
So that's mostly for the. But I mean, you can think about that as like the trough and crest of a wave. The lines on those.
trough 那个峰顶还有峰谷crust and trough 峰谷
Crust and trough.
Yeah. 所以这个地心引力的这个波它的这个波浪呢，它其实是比较像声波，而不是像水波所以它的是有压缩跟这个拉伸的，而不是像水波是垂直这个传递表面的。Yeah. All right.
Yeah.
Wow.
And in fact, you can even hear they turned a couple of the detections into frequencies that you can hear. So you can
hear.
Yeah. So what they did is they just took the wave signature that we got from the gravitational wave and transposed it into
a sound wave.
So basically, all you hear is a little blip. So
I think I've heard that sound file.
If you probably have. So if you don't know what you're listening to, it doesn't sound very impressive. When you do know, then you're like, oh, that's pretty amazing.
Wow.
That comes, the increase in the frequency in sound comes from the increase in the frequency in the compression and of the wave. So of course, as the two black holes get closer and closer, the wave signature has higher frequency.
它的声音就像那个不，那个不，很小声音。
Yeah. So that's all pretty cool stuff. But I suppose the last question is to think about why do we care about this? Why do we care about these things going way out in space?
Out of curiosity.
Yeah. Well, we do. I mean, we do have curiosity. When black holes, when the first solution to Einstein's equation was written down that had something like a black hole. Yeah, it's called the Schwarzschild solution. Don't ask me how to spell that.
Schwarzschild.
A soldier in World War I, actually in the trenches, wrote down a solution to Einstein's equation that had some interesting properties. And at
in
first
World War
II?
World
War I, sorry.
World War I, like when he was still fighting? Or?
I believe he was in, because I believe he died actually in the course of the war. Schwarzschild, if I remember correctly.
一战在算出这个东西，还在壕沟里面在算出这个东西。
But yeah, he was able to write down a solution that described basically a black hole, a place where gravity was so strong that nothing could escape, and so it wasn't clear at that point that anything like that could exist, and now we have very good evidence that they can exist. The first evidence, since we can't see them, as we've already said, came from tracking stars, basically, that we could see were orbiting something really, really closely, but it didn't look like there was anything there. And so
it looked like one star? Or like
just one star orbiting something really, really closely. Right?
Okay,
so two stars orbiting one another. If they're going to keep orbiting and not collide, at least not very quickly, they have to orbit at quite a distance from each other. But there were some observations of a star that was orbiting something really closely, a very tiny, tight orbit.
And it didn't add up. Like
it didn't add up, right?
Star,
there wasn't another star.
One star absolutely
that we could
wouldn't
see.
add up. Yeah.
Yep. That's
two
right.
stars, probably the speed or something, or the centrifugal force.
Yeah, so there's a lot. Yeah, there's a lot of different things we can measure there. So now we have good evidence for black holes. We have good evidence that they collide. But yeah, why should we be curious about this? It just seems cool.
Yeah.
And of course, there's practical implications. This technology we use for the interferometers could potentially be used in a number of other applications. Medicine and communication are always the two that are kind of at the forefront, vying for everyone's
但是也可以用在医学上。
attention.
通讯。
But no matter where our interest in these things comes from, it should be said that really the Christian worldview is the only one that gives us a good motivation for this.
动机。
And quite simply, that's because there was a creator who not only created all of these amazing
造物
things
主。Yeah.
that remain mysterious to us, but created them basically for us to find out. There's a verse in Proverbs that says something very similar to, it's the glory of God to hide things, but the glory of kings, probably take that as humanity in general, it's the glory of men to seek out those things, discover those things. And in doing so, of course, we are...
To discover, like this.
Yeah, in doing so, we learn things about our Creator. So...
That's a good... Could you say that again, or that verse?
Yeah, it's the glory... I think it's in Proverbs 22. I'd have to double check. It's the glory of God to conceal a matter, but the glory conceal. Of kings to seek it out. I think that's the language that the ESV uses. And so God not only created those things, but created humans to discover those things. And did so in a way that we're reminded that there are things way beyond our control, black holes, for instance, but these are things that are still well within his control. And so we can be reminded of those things. We're driven by this curiosity he's given us to find out about all of these things.
Well, I couldn't find it. Yeah. Oh well.
Okay.
Yeah, trying to find the verse.
We'll see if we can find it.
Yeah.
Yeah, and it's given us not only eyes to see the stars at night and be amazed, but even has given us math to be able to write down equations to
like
determine.
Our rationality.
Yeah, even our rationality itself, right? There's no inherent reason why the same kind of concepts that we use to count eggs at breakfast could describe how planets move around the sun, how black holes move around.
I've always been like thinking about like this question. Like the more we study like mathematics and like or any and then in the fields in physics, like we think of these two like as very similar fields because they're like STEM fields. Right. But actually, I think the ancient people, they actually thought these two were like antagonists to each other. Like
sometimes
math is like pure rationality. And
right.
Physics is like sometimes it fits, but then it's kind of like nature.
Yeah, the ancient draw to math was in part that it seemed very, very separate from life. There are things you could do with numbers. There's a branch of math called number theory.
Number theory, 数论.
That the ancient people did a lot of work with, some of which we still use, and seemed for much of history to just be an abstract thing. These are questions we wonder about numbers, and we have different ways of finding them out. But number theory is essential now for cryptology.
密码学, cryptology.
Yeah, so security things.
So what's number theory like? Could you just briefly describe?
What is number theory like? Number theory mostly has to do with
the
properties of integers.
Integers,
so
okay.
Which integers are divisible by one another? How can we know that?
Okay.
And particularly things like solutions to integer solutions to equations. In algebra, we're used to writing down an equation, and we don't care if the answer is a half or a third or an irrational number. But the ancient people kind of almost in some senses kind of revered the integers, and so we're more interested in when can we find integer solutions.
They're probably like
to equations
as bizarre as, or like to them probably these fractions would be pretty bizarre.
The history of math has some bizarre things in it that now we don't think of bizarre. Fractions are one. Zero.
Yeah.
Actually, zero as a number, and then the
imagine
negative.
Zero being bizarre.
Right, and then the negative numbers.
That's
And then, of course, the complex numbers, the imaginary
numbers.
The real numbers.
I love these names, like the rational, irrational.
Right.
Like they really show the whole. We don't know what to name this, and they just keep going towards the bizarre.
Right.
Yeah.
The quaternions is a step beyond the complex numbers.
Okay.
I don't know if you've heard.
I've never heard of
not,
quaternions. Wow.
Yeah. So kind of like
It's getting scary now.
I squared is -1. The quaternions have multiple properties like that, and I don't remember off the top of my head
quaternions.
But basically, so you can think of the complex numbers as still in a plane, right? The imaginary is one direction, and then the real are the two other directions. So the quaternion just extends that into 3 dimensions.
That's scary.
So yeah, you can look.
I'm gonna look that up.
quaternions
Yeah.
and, it's kind of fun. I don't remember that much. I don't even remember which class I was introduced them in and what we used them for. But
anything that goes negative. I mean, even though we 复数这负就是0以下的数字 even though we might think like we should be pretty used to negative numbers, but I know that like in some of the physics that I'm studying, it's scary to see like negative energies or negative anything pop out, because like it doesn't make like you kind of have to interpret it somehow, and it makes it really weird. So we're still not that used to negative numbers. Yeah. Oh wow. Talking about you need this creator to explain like how is it that we all these math we think in our heads like they can actually be used to do any work at all in observations and calculating stuff.
And be useful. Why should math be useful? You can say, oh well, I mean, humans came up with a way to count things. Man, maybe that would be useful if we just
counting rocks.
Came out of counting rocks.
Here's 2 rocks and 3 pebbles.
But yeah, money. that same kind of system works for a whole lot of different things, describing any physical phenomena. And so yeah, that's really
like math
really
all the way,
math,
threads throughout the whole world.
Math all the way down. Though very sophisticated math, right? Calculus takes a notion of infinity that it took us quite a while to grasp or tame, if you want to think about it that way. It took us a while to tame infinity so that we could use calculus, basically make calculus useful.
Like these infinitesimal values.
Right. Derivative things infinitesimally small. 微分, the integral, infinite numbers of areas at the kind of the most basic level.
Well, thank you for talking about these black holes. I know they use like some pretty sophisticated math, and it would be pretty. It probably would be faster for our audience to just go ahead and maybe find a physics book that talks about the actual mathematics. It's already hard enough to write it out like on paper. Probably it's even harder to like explain it. Yes. Well, thank you, Tyler Knowles, for having this gravitational, very very attractive topic. 非常吸引人的一个话题。So that's all for our gravitational waves. Is there anything you might want to tell the audience as a final aside, or any thoughts? Just free.
Well, first, I mean, thank you. I appreciate the opportunity to share some of these things. But
black holes.
Stay curious, I guess, and don't be afraid to.
Stay hungry.
Don't be afraid to stay curious, but also stay humble and remember the Creator who has graciously given us the curiosity and the world to discover.
Amen.